Hello everyone, welcome to Geeks Gate Computer Science channel. I'm your instructor Joy. So our today's topic of compiler design. So our subject is compiler design, and today we will be discussing about the previous year questions on the special topic of code optimization and code generation. So before going to start my lecture, please comment and let me know whether my audio and video is working properly or not. Please comment in the comment section so that I can understand that my audio video is working properly or not. Okay, so I'm getting comments. Okay, it looks good. Okay. So we are starting our session. So our first question is the GATE 2017 set 1 question. So here you can see, let me change the color of the ink first. Okay, so here you can see the intermediate program, the intermediate code, that is a 3 address code, is given here. Okay, so we need to find that which one of the following corresponds to a static single assignment from the above code. So firstly, before starting the question, we should know about what is called the static single assignment. Okay, so the static single assignment means in the temporary variables. Suppose in our 3 address code we use multiple temporary variables, right? So here all the temporary variable, in case of all temporary variables, we can assign a value to a temporary variable only once. Okay, suppose I am telling that t1 is equal to a plus b. Okay, now again I cannot tell that t1 is equal to t1, the same t1 is equal to b plus c. Okay, because here you can see the t1, this t1 variable is assigned 2 times. Okay, so t1 variable is assigned 2 times, that we cannot perform because it is a static single assignment. Okay, single assignment means we need to we can assign the value to the variable only once. And static means before starting of the programming, okay, before starting execution of the code, we need to assign those variables. Okay, and static means what? That throughout the program flow, suppose the program flow starts from here, ends here, so throughout the program flow, the variable will be there in the space. Okay, suppose this space is given to the variable t1. Okay, so the space will be with the variable with beginning at the programming and at the end of the program. Okay, up to at the end of the program. Okay, so throughout the execution of the code, the variable will have some space. Okay, it will occupy some space. So that is called a single static assignment. Okay, now here in the given code you can see these are all variables. Okay, these p, q, a, b, u, v, these are all variables. Now you can see that p, this variable is assigned 2 times. Okay, the variable p, that is assigned 2 times. So firstly we need to discard this one. Okay, and secondly the variable q, this is also assigned 2 times. Okay, then we also need to discard. So first let's trace all the options. Firstly option A. So in option A we can see the variable p1 is assigned 2 times. Okay, variable p1 is assigned 2 times, as well as variable q1, it is also assigned 2 times. So it won't permit our condition. Okay, our condition is what? It should be the single static assignment. Single assignment should be there, but here we can find that a single variable is assigned 2 times. So it is not permitting our condition. So option A won't be the option. Now checking the option C, here you can see that P1, Q1, P3 and Q2, these 4 options are, these 4 variables are assigned only 1 times. Okay, so according to the condition, the option C should be the correct, this should be the correct option, but we need to find whether the same flow control, same data flow control is also followed here or not. Okay, so firstly we can match one by one. Firstly this p equal to a minus b, so here instead of p, the option C is telling p1, so p1 equal to a minus b, that is perfect. Now second statement is saying that q equal to this p. Okay, this p, this value is coming here, so p tends to, the value of p is going to here. Okay, the value of p is going to here multiplied by c. But here in the second statement, we can see in the second statement it is telling p2. Okay, but in the first statement the value is assigned to p1. So we don't know that what this p2 is meaning. Okay, p2 is not a, it it is not yet initialized. Okay, so we don't know what is P2 because the value was assigned previously to P1, right? So according to the flow of graph, or you can say according to the data flow, this is not correct. Okay, so we are also discarding this option too. So now next checking the option B. Okay, now let's check this one. Firstly, we should check whether some variable is assigned twice or more than twice. We need to check. So here we can see that P3 is assigned once, Q4 is assigned once, P4 is also assigned once, and Q5 is also assigned once. Now the second thing is that we need to check whether the flow of data is working correctly or not. So firstly, P3 is used instead of this P. So P3 is A minus B, that is correct. Now Q equal to P, this P, Q equal to the value of this P multiplied by C. So here we have used P3, right? So P3 will be used here instead of the P. So P3 multiplied by C, that is also correct. Next, the new variable P4, the next, new variable P4 is also used, and that is equal to U into V. It is not dependent, so that's fine. And now Q5 is equal to this Q4, Q4 as well as P4. Okay, Q5 equal to this P4 as well as plus Q4. So here the same is there, that Q equal to P plus Q. So value of P will be taken from here and value of Q will be taken from here. Okay, so the second statement and third statement, the addition will be placed here. So it is the same flow of data is also mentioned here. Okay, it is also been followed. So option B is going to be the correct option. Now let's check the option D also for the sake of performance. Okay, so here we can see all, here you can see that P1 is equal to A minus B, that's correct. Now Q1 is equal to P. Okay, so here in our original statement you can see this P is actually taking the value of from the first statement. Okay, but here in the first statement the assignment operation was taken to P1 only. Okay, so now we don't know that what this value P is going to express. Okay, but this variable P is going to contain, we don't know, so it is not following our data flow. Okay, so the option D won't be the correct option. So the only correct option is being the option B, right? So for this question the correct option is option B. Now moving forward to the next question, it is also a GATE 2017 set 1 question. Let's take the pen first. Okay, so it is saying that consider the expression A minus 1, then here B plus C divided by 3 plus D. Let X be the minimum number of registers required by an optimal code generation. Okay, so minimal number of register we need to find. Algorithm for a load store architecture in which only load and store instruction can have memory operand and arithmetic instruction can have only register or immediate operand. Okay, it means that any register, okay, it means that for any arithmetic operation should not have any kind of variables. Okay, it means that we cannot write like this. Suppose I am telling that r1 is equal to x plus y. Okay, we cannot write like this because there are two operands. Okay, so we cannot take memory operand. Okay, because these are two variables, right? These are not immediate operand. What is immediate operand? That should be some constant. It can be 5, 6 or any integer. Okay, so but here this x and y, these are not immediate operand. Okay, these are the memory operand. So here so we can say that this type of operation won't be there in our code. Okay, so everything for every variable, first we need to place it into we need to load it into some register and then we need to use it. Okay, so here in the given expression, first thing that we need to follow, or the first operation that we need to follow, that is the B plus C. Okay, so let's use some registers. Okay, firstly let's take the register 1 and it is taking, or it is assigning the variable B. Okay, so it is taking the value of B. Now let's take another register T2, it is also taking the value of C. Okay, now let's take this T1 itself. Okay, T1 itself, and it is taking the value, let's say it is, T1 will take this B plus C. Okay, T1 will take B plus C, so we can write like this: T1 is equal to T1 plus T2. Okay, the resultant of this T1 plus T2 will be placed to the variable T1. and next whatever the T1 is containing, it should be divided by 3, and 3 is some immediate operand. Okay, so we can take it. So immediate operand is applicable. So T1 is equal to T1 divided by 3. Fine. Now the next thing is that this the whole value should be added with D. The whole value should be added with D. So we cannot write, see, this T1, we cannot write the value of T1 plus D. Okay, we cannot write like this because D is not some immediate operand. Okay, so what we need to do, we cannot write like this. So what we need to do, we can take the value D. Okay, we can take the variable D to the other register, that is T2, and next we can do this operation. Okay, T1 is equal to T1 plus T2. Okay, in this way it is adding the resultant of this T1 to with D. Okay, so it means that our this part, okay, our this part is already completed. Now what is next? The next is that this A minus 1. Okay, so let's take the T2 itself. We can use the T2 itself where we can assign the value 1. I mean, we can assign the variable A. Okay, now T2, we can do this operation because it is an immediate operand. Okay, the 1, it is a constant, right? So we can follow this operation. Okay, so this is fine. So now T2 is containing the left part, and T1 it is containing the right part. Okay, so our final resultant, we can either place it into T1 or T2 anyway. So that we can write like this: T1 is equal to T1 multiplied by T2. Okay, so this is going to be our final result. Okay, so our final result will be stored at the register T1. Now you can see that the whole expression we have covered using only two registers. One is the register T1, another is the register T2. Okay, so the whole operation we have covered using only these two registers. So the question is asking that minimum number, right? The minimum number of register required by the optimal code generation. So minimal number is what? Minimal number is obviously 2. Okay, so 2 is going to be the minimal number for this question. Now let's check that what is in the third question. So it is a question from GATE 2017 and it is a set 1 question. Okay, so firstly let's see, it is a grammar is there. Okay, up to here a grammar is there. So it is telling that where relob, okay, relob is a function, okay, is a relational operation. Okay, example like this, and this null is referring to an empty statement, and null is referring to the empty statement, and if then else are terminal. Okay, if then else, these are terminal. Consider a program P is following the above grammar containing 10 if terminal. Okay, the program P, okay, the program P, it is containing 10 if terminals. Okay, it is containing 10 if terminals. Now the number of control flow paths in P. Okay, how many control flow path is P? Is there in the P. Okay, so for example, it is given that if this type of question is I mean statement is there, that if expression E, okay, so if expression E is giving true, then we need to go to E2, or if it is giving false, if the expression E is giving false, then we will go to E3. Okay, so there will be two paths, one is E1 to E2 and another one will be E1 to E3. Okay, two paths. So now we need to find that number of control paths in our program P. Okay, so for this, firstly you need to understand that how this if statement is working. So if, I mean in the C program or any program, if you use the if statement, so you need to provide some condition here. Okay, so if the condition is true, the result of the condition will be either true or false. Okay, if the condition is true, we should redirect to some statement. Let's write it. E1. Okay, so if the condition is true, we are going to E1. If the condition is false, we are going to E2. Okay, so for every if statement, you can see two paths are there. Okay, so for every if statement you can see two paths are there, right? And here in our given program, you can see that it is containing 10 if terminal. Okay, it is containing 10 if statements, right? So for 10 if statements, if a single if statement is giving 2 paths, then 10 if statements will give how many paths? It will give 2 to the power 10 paths, right? If a single if statement is giving 2 paths, then 10 if statement will give 2 to the power 10 paths. So our answer will be 1024. Okay, so we will have this 1024 paths. Okay, so if you have any question regarding this, you can put it in the comment section. Okay, if you have not understood anything, if you have any doubt or something, you can put in the comment section. Okay, okay, so I'm seeing the comment. Okay, so let me explain it again. Okay, suppose let's first clear this part. Okay, see, one thing is there that in the level 0, okay, if you talk about all the level of if statements, so in the level 0, suppose we have some statement e1, okay, then in the level 1, this e1 will give us two paths, right? It will give us two paths, suppose e2 and e3. Okay, so in level 1 we are having 2 to the power 1, we have having 2 to the power 1 paths, like, right? So in the same way we will go up to the level 10, because it is saying that how many if statements are there, we have 10 if statement, and here in the level 1 we have how many if statement, we have only one if statement. Okay, so one if statement level 1, so 10 if statement means level 10. So level 10, how many paths will be there? The paths will be 2 to the power 10. Okay, this is a very easy concept, right? I hope that you are getting the point now. Fine. Okay, so I'm moving forward. So this is a question from GATE 2016 and it is a set 2 question. Okay, so GATE 2016 set 2 question. So it is saying what a student wrote two context free grammars G1 and G2. So here two grammars are there, G1 and G2, for generating a single C like array declaration. Okay, so this is a array declaration of C. Okay, and this grammar should basically generate this array. Okay, so the grammar use D as the starting symbol. Here we can see that D is going to be our starting symbol, and there are 6 terminals. Okay, what are those terminals? The int, then semicolon, id, starting braces, ending braces, and num. Okay, so these are the 6 terminals the grammars are using. Okay, so basically using this grammar we need to find whether we can generate this array, I mean this array declaration statement or not. Okay, so firstly starting with the grammar G1. So checking the grammar G1, in grammar G1 we have D. Okay, so from D we are basically starting. So it is giving us int L. Okay, so this first int is generated. Now our next target is to generate this A. So A is basically a ID, right? A is basically ID. So we can use our second production rule. Suppose I am giving the numbers. Okay, the first production rule, second production rule, third production rule, and fourth production rule. It will be easier to like express. So I am let's use the second production rule. Okay, so instead of this L, we will place what? We will place ID, uh, starting braces, and E. Okay, so we have used the second production rule. So we can see that after the starting braces, it should be some number should be there. Okay, so we need to use the third production rule. Okay, so if you use the third production rule, it should be ID, and instead of this E, we will place num and closing braces. Okay, so num and closing braces. So if we are using this production rule 3, then it will be at the end. Okay, it will be at the end, and we cannot generate the next number. Okay, we cannot generate the next statement, that is 3. Okay, so it won't be the correct one. So option, I mean we cannot use the production rule 3, we should use the production rule 4, because after using the production rule 3 we cannot find any terminal. Okay, there is no terminal, so we I mean sorry, there is no more variables. Okay, so if there is no more variable, then we cannot move forward, right? So we should use the fourth production rule. Let me first delete this one. So ID, okay, So id starting braces up to this part was there. So instead of this e, we are writing the fourth production rule. So num closing braces, then again starting braces e. Okay. So let me write it again. Here we have used the production rule 1, production rule 2. We have used here production rule 3. Now after this e, now we can close. So we can use the production rule 3. So this was the production rule 4. Now we can use the production rule 3. Okay, it was already there, and instead of this e, we can place num and closing braces, right? So num and closing braces. So now you can see our the array declaration statement is generated. Okay, array declaration statement is generated. So grammar G1 can generate the array declaration statement. Okay, grammar G1 can generate it. Now let's check whether the grammar G2 can generate this one or not. Okay, so for this was for grammar G1. Now let's check for grammar G2. So grammar G2 also, our starting symbol is what? Starting symbol is D. Okay, so D2 we have only one production rule. So D2 integer of L. Okay, so we have only one production rule. So this is the production rule 1. Let's number it again. Let's number it using 1, 2, 3 and 4. Okay, so this is fine. The it is the correct one. Now the next thing is that we should generate the id. Okay, id for this variable a, right? So in place of this L, we can use the production rule 2. So in place of this L, if we are using the production rule 2, so that will something look like IDE. Okay, IDE, and we are using the production rule 2, right? Now after that we need to generate this two starting braces, ending braces with the number. Okay, so if we follow the production rule 4, it will just generate a single number. Okay, it will give us a single number and it will be ended there, because there is no other variable that is left. Okay, so as there is no other variable, so only the fourth, I mean, then we cannot use the fourth production rule. Okay, so we need to use the third production rule. So third production rule is saying what? It is in place of this e, we can place e then num. Okay, so in place of this e, we can place e and num. Okay, and our semicolon. So it is the third production rule, you can see, right? And now we should, I mean, this 3 is already generated here. Okay, because the ending number is generated. Now for this 10, we need to follow the production rule 4, and now we can end basically, because we don't need to move further. So num and num. Okay, so this is the fourth production rule we are using, and in this way our I'm just giving the semicolon, and in this way you can see our given array statement. Okay, our given array declaration statement is actually generated. Okay, so basically we can generate the statement using the grammar G2 as well as grammar G1 also. Okay, so grammar G1 and grammar G2. So using both the grammars, the question is what? The question is that which of the grammars correctly generate the declaration mentioned above. Okay, so G1 and G2 both can generate the declaration mentioned above. Okay, so both grammars can generate this one. So moving forward to the next question. Okay, so this question you can see it is a GATE 2016 question, and it is taken from the set 1. Okay, so it is telling what the minimum number of, it is a, suppose it is a 3 address code. Okay, 3 address code is given here. So minimum number of total variables required to convert the above code statement to a static single assignment. Okay, so it will also be some static single assignment, and we need to find the minimum number of variables. Okay, static single assignment is there. So in static single assignment also we cannot do this operation, right? So basically for this u minus t, okay, let's talk about, I mean, one by one statement we can execute. So firstly here right side, what are the operands? The operands are u and t. Okay, the operands are u and t. So firstly let's take the variable r1. Okay, so r1 is u. let's take R1 is U and R2 give it as T. Okay, R2 we are giving T. So R3 that is equivalent to the variable X. Okay, R3 it is equivalent to the variable X, so that is equal to R1 minus R2, because R1 minus R2 is giving U minus T. Okay, U minus T is there. Now this Y. Okay, so before using Y we should find that whether this variable B is there or not. I mean variable B, it is not yet initialized, right? So R4 we are giving R4 to the variable B. Okay, so whatever the value this variable B is containing, we should place it to the register R4, or you can say the temporary variable R4, right? Now let's talk about R5. So R5 is taking what? It is taking the value of X that is coming from here and multiplying with B. So value of X is basically here in R3 multiplying with R4. Okay, it is multiplying with R4. Now so this statement is also got completed. This is basically the Y, it is representing Y. Now the variable X. Okay, so the variable X is taking what? It is taking Y is coming from here, and W we have not initialized W. Okay, so firstly the first thing is that we should initialize W. I mean we can place the value of this W to some register or some, you can say the total, I mean temporary variable R6, right? Now this X, okay, suppose this X, so we should initialize some another temporary variable R7 is equal to Y. So Y is basically this R5, right? Y is basically this R5 plus this R6. Okay, Y is basically R5 and plus R6. So our third statement is also executed, and R7 is representing the value of X. Okay, now this Y, okay, so this Y is basically taking T and Z. Okay, so let's give R8 to T, let's give R8 to T and R9 to Z, because these two are very much new variables. Okay, these are very new variables. So R8 to T and R9 to Z, right? Now this Y we should need to write it. So firstly see, okay, there is some issue that this T, okay, this T we have already assigned and the value of T is not yet changed. Okay, so T we have already assigned, that is what? That is R2, right? So T we have already assigned, that is R2. So let me just delete this one. So in R8 basically, we can assign Z, because Z is the new variable, T is already assigned, right? In T is already in the temporary variable R2. Okay, so Z we are putting to R8. Now R9 is going to be our R2 plus this R8. Okay, R2 plus R8. R2 is taking what? R2 is taking T and R8 is taking Z. Okay, so T minus Z. So let it be, it is going to be minus. Okay, so T minus Z is going to be here, and R9 is representing basically the variable Y. Okay, so R9 is representing the variable Y. And lastly this statement, the last statement, it is taking the value of X from here and Y from here. Okay, it is taking the value of X from this third statement and Y from the fourth statement. So let's take another temporary variable R10, and it is taking the value of X from R7. Okay, so from R7 it is taking here, and from R9 it is taking the value of Y. Okay, so R9 it is taking the value of Y, R9, right? So and the multiplication will be placed at R10. Okay, the resultant of the multiplication will be placed at R10. So the question is what? The minimum number of total variables required to convert the above code. Okay, total variables means all of these temporary variables we are using. Okay, so total how many variables we are using? We are using 10 variables. Okay, 10 total variables we are using in our given code. Right, I hope that you have understood. Right, now if you have any question or doubt, please put it in the comment section. Okay, if you find any issue, any question, any doubt, please put it in the comment section. If you are watching the video after the live session itself, so that you can also place your doubts in the comment section, me or our team will get back to you with the problem, I mean with the correct explanation. Okay, so that's fine. Now till now it looks good. So I'm going forward to the next question, that is the GATE 2015 question, and it is taken from the GATE 2015 set 2. Okay, so basically it is a in the context of abstract syntax tree. So firstly, what is the abstract syntax tree? So syntax tree, you know that it is a parse tree, you can say, which is taking all the syntaxes. Okay, it's a parse tree with all the syntaxes, and it is a abstract. Okay, abstract means basically we cannot see the data, so actually. Okay, so I mean, whatever inside the tree or whatever inside the data we cannot see. So this is just the abstract syntax tree and control flow graph. Okay, so which one following is true? So firstly, let's check the option 1. So in both AST and CFG, let node N2 be the successor of node N1. So N2 be the successor of N1 means N1 is the predecessor and it is going forward to N2. In the input program, the code corresponding to N2 is present after. Okay, so it means that if the graph looks like this, okay, that N2 is the successor of N1, then in the code itself N2 should be after the N1. It means in the code itself N2 should be after N1. So N1 should be at the before and N2 should be at the. So this statement is not always correct. Okay, so this statement is not always correct. Suppose our this is our starting symbol. Okay, so from here we are starting, we are going to N2 and then we are going to N1, and suppose we are going to end it. Okay, so from starting we are going to N2, then N1, then end it. Okay, but there is some another path, which is going from N1 to N2. Okay, there is some another backward path which is going from N1 to N2. So in this way N2 is going to be the successor of N1. Okay, N2 is going to be the successor of N1, but if you see the code flow, then it is starting from the starting symbol S, then it is going to N2, then it is going to N1, and it is going to be end. Okay, so as there is some backward path is obviously possible. I have talked about multiple control flow graphs, so you can take the example. So backward path is obviously possible in the control flow graphs. So here actually, instead of this N2 is being the successor of N1, in the code itself you can see that N2 is not actually after N1. Okay, it is before N1. So the first statement, it is not the correct statement. So we are just I mean, this false, right? It is not correct. So let's check the second statement itself. For any input program, neither AST nor CFG will contain a cycle. So cycle can obviously be there, right? Here we have also talked about some cycle. So cycle is, I mean, it is obviously possible. So option C is not the correct option. The next one is that maximum number of successor of a node of an AST and CFG depends on the input program. So this option is going to be true because we are checking the third option, right? So this option is going to be true because the maximum number of successor, okay, the number of successor is basically dependent on the input program, because in the input program is what which is deciding that how many, I mean, how the flow graph will look like. Okay, suppose we have some input program A1, so there will be some specific flow graph for this program A1, right? And this program itself will decide that how many nodes will be there, how many edges will be there in the flow graph itself. Okay, so the maximum number of successor of a node in an AST or CFG depends on the input program. That is obviously true. Okay, it is I mean, the flow graph is dependent, right? And checking the fourth option, it is telling that each node in AST and CFG correspond to at most one statement in the input program. Okay, each node in AST and CFG corresponds to at most one statement. Okay, so this is not correct, that at most one statement is not correct. In a specific node, okay, in a specific node we can have multiple statements. We can have statement 1, statement 2 as well as statement 3, and we can have multiple other statements, right? So there is, I mean, it is a possibility is there that there can be more than one statement is in a single node. Okay, so option D is also a wrong option. So the only correct option is going to be the option C, and it is going to be our correct option, right? I hope that it is clear to you. If you have any doubt, you can always put it in the comment section. Okay, fine. Now I am going forward to the another question. This question is taken from GATE 2015 and it is also a set 2 question. So let's see. The question is that consider the intermediate code given below. So it is an intermediate code given below with some go to statement is there, and the number of nodes and edges in the control flow graph constructed for the above code respectively. Okay, so we need to find the number of nodes and number of edges will be there in the control flow graph. Okay, so to make the control flow graph, I told you in the previous, like in the content videos, I told you that to find the control flow graphs we need to find the leaders. Okay, we need to find the leaders and eventually we need to find the blocks. Okay, we need to find the basic building blocks, and after that we can give the flow generation. Okay, so to find the leaders there are basically three ways. One is the, I told that it is the first statement. Okay, first statement, then target of go to, it will be another leader, and the third one is going to be the statement after go to. Okay, statement after go to. So in this way these three types of leaders can be there. So first statement, the option, I mean 1 is going to be our first node itself. Okay, option 1 is going to be, I mean the statement 1 is going to be our first node. Okay, so from there you can see 2. Okay, node 2 is basically a target of a go to. Node 2 is basically a target of a go to, right? So node 2 will be in another node. Okay, now from node 3 to up to node 8, from 3 to up to node 8 you can see there is no more conditions. Okay, from 3 to 8 there is no more conditions, so we can place this 3 to 8 in a single node. Okay, so 3 to 8 there is no more condition, so we can place this one up in a single node. Now in node 9 this is a go to statement. Okay, so this is a go to statement, it will be in another node, right? Now what is after this go to statement? The statement after a go to statement, that will also be a building block. So 10 is going to be also a building block, right? And finally 11 is also a go to statement. So go to statement, target of go to, and whatever statements are after this go to statement will also be some another blocks. Okay, so in this way we have these 6 blocks, 6 building blocks, or you can say 6 nodes. Okay, we have the 6 nodes, and now the next statement, next thing is that we need to find the flow of graph. So it is 1 to 2, that is fine, 2 to 3 it is also fine, 3 to 8 it is going right. So 9. Okay, in 9 if the condition gets satisfied, okay, 9 is saying what? 9 is saying that j less than equal to 5 is the condition. If the condition is getting satisfied, then it will go to the statement 3. Okay, it will go back to the statement 3. So it will go back to the statement 3. Here another path will be there. 9 to 10 it is fine. Okay, if the condition gets false, okay, if the condition is not true, then it will go to node 10, right? From node 10 to node 11 it is obvious because there is no more path, I mean no more go to statement. But in 11 there is an go to statement, right? And it is dependent upon this condition, I less than 5 should be there, so go to of 2. So in 11, from 11 if the statement is, if the condition gets true, it will go to the node 2. Okay, so this path will also be there. So overall how many nodes are there? So how many nodes are there? 1 2 3 4 5 6. So 6 nodes we are finding. And how many edges are there? So edges we can find 1 edge, 2 edge, 3 edge, 4 edge, 5, 6 and 7 edges. Okay, so total 7 edges and 6 nodes are there. So option B is going to be our correct option, right? Option B is going to be the correct option for this question. If you have any doubt, you can place a comment in the comment section. So good. So we are moving to the next question, and it is a question from GATE 2015 set 1 question. So GATE 2015 set 1 question. So this is a GATE 2015 set 1 question. Let's see what this question is telling. A variable x is said to be live at statement si in a program if the following three conditions hold simultaneously. Okay, so variable will be live if these three conditions get satisfied. So what are the three conditions? There exists a statement sj that is using the variable x, and there is a path from si to sj in the flow graph corresponding to the program. There is no path intervening the assignment to x including si and sj. So basically it is the definition of the live variable. Okay, we have talked about that how a live variable will look like. So this is a basically a definition of the live variable itself. Okay, so it is, I mean, the definition is telling that suppose there is a statement 1 where we have generating the I mean the variable x is there, and now there is some another statement sj after this si. Okay, and it is using the variable x. Okay, it is using the variable x, and there is no intervening assignment to the variable x including si and sj. Okay, so in that case only we can tell that the variable x is live at si because it is used after this si. The x is used after this si, so that is why we can write like this. Okay, so this is our given question is there. Okay, let me change the color. Okay, so in our given question we have 6 statements basically. Okay, there are 4 blocks, right? There are 4 blocks and we have 6 statements. So let's write all the statements. This, suppose this is statement 1, statement 2, statement 3. Now let's take the statement 4 here, statement 4, statement 5, as well as let's write this is the statement 6. Okay, so there are 6 statements. Now the question is telling the variables which are live both at the statement in basic block 2 as well as the statement in basic block 3. Okay, so in basic block 2 and 3, in this and this, some variable should be live. Okay, so we need to find. So first of all, we can check one by one. Okay, so how many variables are there? You can find there are p is there, q, r, s is there, p, q, r, s, and I think u, v. Okay, p, q, r, s, and u, v. So u, v, p, q, r, s. These 6 variables are there. Okay, 6 variables are there. So firstly, let's check with. I mean, let's write uv here. Okay, because it is just clearing the position. Okay, so these 6 variables are there. Okay, now let's start with the variable p. Okay, let's start with the variable p. So here you can see that from this 1, I mean this 2, okay, this 2 and 3, here you can see. So basically in this block 2 and 3, the variable p is not used. Okay, the variable p is not used. So after this, variable p is not also used in the block 4 also. Okay, in the block 4 the variable p is also not used, but there is some path from the variable, I mean from the block 4 to the block 1, right? This path is there. So here in this path we can see in the statement 2. Okay, so in the statement 2 this variable p is being used. So firstly, from this statement 4 as well as from the statement 5, there is a path that we are going to the statement 2. That is correct. But in statement 2, whatever the value of p is being used, that is already assigned in the statement 1. Okay, so in statement 2, whatever the value this p variable is using, that is assigned by the statement 1. So it is just discarding, or you can say it is disfollowing our condition 3, because condition 3 is saying what, that there should not be any intervening assignment to x, but it is having some intervening assignment, right? So so like P won't be live, P won't be live in block 1, I mean block 2 and 3. Okay, so we are just discarding P, so P won't be live. Now let's check the Q. Okay, so if we check the Q, so there is some path that, I mean, here also, if Q variable is live here, right? So if Q variable is live here, okay, then there is some path, I mean, from for this Q we can write that there is some path that from S4 and S5 we are going to S1 itself. Okay, we are going to S1 itself where the variable Q is being used, but in the way there is some assignment of the Q statement, right? There is some assignment which is changing the value of Q. Okay, there is some assignment of the Q statement which is changing the value of Q. So we can say that the Q variable is not also not live at this block 2 and 3. Okay, now let's check the variable R. Okay, so let's check the variable R. Variable R is being used here, here it is not used. The variable R is also used here, and it is going back to be used at the statement 1. Okay, so from this block B2 and from the block B3 also, variable R is going to be forwarded to the block B1 itself. Okay, but you can see that it is like not used, I mean it is not assigned. Okay, it is not assigned in anywhere. So you can say that yes, R variable is live because it is not yet, I mean there is no intervening assignment. Okay, so R is live. Now let's check the S. So basically here we are using the variable S. Okay, so here suppose the variable S is there here and here, I mean block B2 and B3, suppose the variable S is there. So in B3 we are using the S, fine. So statement S6 is not changing anything. Now we are going back to the block 1. Here in the statement S2, we can find some assignment. Okay, so in the statement S2 we can find some assignment. After that in state 3 the value is going to be used. Okay, so in state 3 the value is going to be used, that is fine, but it is using the assigned value which is assigned in the statement 2. Okay, it means that it is disrespecting our third rule. So the, I mean the variable S is not also live here. Now checking for variable U and V. So variable U and V, we can see that these both are in use here. Okay, I mean both of these U and V are used here, but that is not assigned, that is fine. Now going back, so basically you can see that variable, so basically you can see that variable V. Okay, let's talk about firstly the variable V. Okay, so variable V here is basically assigned. Okay, variable V here basically assigned, and if we say that the variable B is live here, but it is assigned. Okay, so before using the value here, the variable V is assigning. Okay, so it also won't be the live variable. Now left it only U. So we should check whether U is assigned or not. So here we can find that U is not assigned, it is being used. And in these two statements also, I mean S4, S5 and S6, the variable U is not assigned. Now going forward to here, basically here we can see that U is actually assigned. Okay, U is not used. The variable U, it is not used, it is being assigned. Okay, so we can say that whatever the value the U is containing, that is not used in this statement S3, right? So in that way we also can say that U is not live because U is newly assigned, it is not live here. Okay, so only variable that is being used, okay, or that is being live at both B2 and B3. Okay, the variable that is both live in B2 and B3, that is the variable R. Okay, so what should be the correct option? So the correct option is not containing R. I mean there is no option that is containing R, but R should be the correct option. Okay, so in these cases if all the options are wrong, Okay, here my understanding is saying that all the options are wrong. So if in any cases, if the all options are wrong, then you can mark only, I mean, some of the option which you feel that that is going to be the most appropriate option. Okay, you can mark it, or you can also, like, you can also leave it. The gate authority will provide the marks to each and every student if all the options are being wrong. Okay, so fine. So I hope that this question is clear to you, right? If you have any doubt, you can put it in the comment section. So now going forward to the next question, it is also a GATE 2015 set 1 question. Let me change the ink color. Okay. So it is a GATE 2015 set 1 question. It is saying that the least number of temporary variables required to create a 3 address code in the single assignment. Okay. So least number. Again, we can temporary variables it is asking, right? So we can use, so we can basically start from the beginning. Okay, so let's say t1 is a temporary variable, it is taking r divided by 3. Fine. Suppose again t2 is a variable which is taking t1 plus adding with q. Okay, now let's take another variable t3 which is taking the value of t2 and it is adding with s. Again t4, it is taking the value of t3 and it is subtracting t. Okay, t is some constant. Okay, wait a minute, here t multiplied by 5 should be there, right? So t multiplied by 5 should be there. It means that t multiplied by 5. So wait a minute, we should firstly we should do this operation, right? T multiplied by 5, then we can uh, do one thing. So here let's take another temporary variable t4 and it is doing the operation t multiplied by 5, right? And now let's take t5 and it is basically t3. Okay, what t3 is containing? T3 is containing up to this part. Okay, and t4 is containing this part only, t multiplied by 5. So t5, if we say that t5 is the whole thing, then it should be t3 minus t4. Okay, t3 minus t4. So we have covered up to this part. Okay, up to this part we have covered. Now let's evaluate this expression firstly. So t6 let multiplied by u multiplied by v, and let's take t7, it is basically t6 divided by w. Okay, so t6 divided by w, so t7 is the ultimate option that is containing this part. So let's take the t8 and which is adding this t5. Okay, so up to this part it was t5 and this whole part it is basically t7. Okay, so t8 is going to be our final answer and it is t5 addition to t7. Okay, so t8 is going to be our last temporary variable. So how many temporary variables we are using? So how many temporary variables? There are total 8 temporary variables. Okay, so total 8 temporary variables we are basically using, right? Now going forward to the next question. It is basically a question related to the recursion. It is a GATE 2014 set 3 question. So the following statements are correct. Which of the following statements are correct? Static allocation of all data areas by a compiler makes it impossible to implement recursion. Okay, so static allocation is making the recursion impossible. Okay, so for recursion static allocation won't be there. So this is true that for recursion we should use the dynamic allocation. Okay, because in recursion you can see that we use some stack and there will be some activation records. Okay, so there will be some activation records we need to follow and everything will be dynamically allocated. Okay, dynamically allocation should be there, right? Then dynamically allocation should be there. So the option 1 is correct that it is impossible. Option 2 is saying that automatic garbage collection is essential to implement recursion. It is wrong. Okay, automatic garbage collection is not needed. Option 3 is the dynamic allocation of activation record is essential to implement recursion. It is correct, that I was talking about. And 4 is one, the both heap and stack are essential to implement recursion. No, heap is not essential. We can implement the recursion using stack only. Okay, so option 4 is also wrong option. So only option 1 and 3 is correct. So the last option, that is option 1 and 3 is the correct option, is going to be our final. Okay, so it is going to be the correct option. Now moving forward to the next question, it is the last question of today's discussion. The question is on GATE 2014 set 3 question, right? So GATE 2014 set 3 question. So consider the basic block given below. It is the block given the minimum number of nodes and edges present in the direct acyclic graph, directed acyclic graph representation of the above basic block. So this is a 3 address code. We need to convert it to the DAG representation. Okay. So there will be one DAG graph, right? Only one DAG graph should be there, and here we can see 5 3 address codes are there. Okay. So we need to make it, and we need to convert it to a single 3 address code, right? So going forward, A is equal to B plus C. It is the first statement, right? A is equal to B plus C is the first statement. So the next statement is saying that C equal to A plus D, and A is what? The value whatever the A is getting from the first statement. Okay, it is carrying forward to the second statement. So whatever the value of A here it is getting, it is carrying forward to the second statement, right? So second statement is what? C equal to A plus D, and A is what? A is B plus C. So it will be B plus C plus D. Okay, second statement is done. So third statement it is what? So third statement is D equal to B plus C. Okay, so B plus C. So whatever C is containing here we will place here. So C is basically B plus C plus D, we will place here. Now the next statement, fourth statement is telling what? It is telling that E equal to D minus B, D minus B. So D is taking from here, E equal to D minus B. So D is what? D is basically B plus C plus D minus B minus B. Okay, D is E is basically, this is D, right? This is D. So this part is basically D and this is B. So D minus B it is taking here. And the last is what? Last is A equal to E plus B. Okay. So A equal to E. E is taking from here. So this B, 1B we can cut it. Okay. So it is B plus C plus D. Okay. Which is like E. Okay. E equal to what? B plus C plus D plus B. Okay. Plus B is here. So E plus B. So this part is basically E and this is basically B. Okay. So E plus B, and it is our last statement. Okay. So last statement, A is equal to this much. So now we need to draw the directed acyclic graph for this. So we can see here that two B's are getting added. Okay. So plus and two B's are getting added, right? So B is taken by 2 plus, and then we can take the value to add with the variable C. Okay, to add with the variable C. Now whatever the resultant is coming, we can take it and we can add with the variable D. Okay, we can add with the variable D. So B is used twice, then C, then D. So how many nodes are there? The number of nodes 1, 2, 3, 4, 5, 6. So 6 nodes are there, and how many edges are there? So edges we can find that 1, 2, 3, 4, 5, 6. So 6 node. So it is saying the nodes and edges. So 6 node and 6 edges. Okay, 6 node and 6 edges will be there, and this is a directed acyclic graph. So this is end of our discussion of our today's topic. I hope that you have understood and enjoyed a lot. If you find any question regarding this topic or regarding the any of other your queries related to the compiler design, you can put it in the comment section. Me or our team will help you out and will reach you out to give you the correct explanation. Okay, so thank you for joining. Keep looking at the Geeks for Geeks GATE Computer Science channel. Here you will get the free live classes of all the GATE subjects, GATE Computer Science subjects, and the recent updates related to GATE exam. So thank you for joining.